Okay folks, welcome back. This is probably going to be one of the shortest videos of the whole semester, assuming we're using any of these, rather than doing them in class. So we are on the week 2 slides under letter D, properties of matter and changes and all that good stuff. And just go ahead and copy down the first 2 things on your own. You don't need me to do that for you. So physical properties are just something that's inherent, like the way something looks, its color, its malleability, so some of those engineering kinds of properties, its density, its mass over its volume, that's a physical property that's unique to a substance. So that's more of a lab thing. And then physical changes, we already did all of those. So those are the phase changes: condensation, melting, sublimation. So make sure you know all of those and you could describe them on a molecular level. That's really what you want to be able to do with that information, is know the difference between a physical and a chemical change. And also what you see up there, hopefully written on the board, is an abbreviation. Like chemical change is also known as a chemical reaction, and an abbreviation for reaction is RXN. So I'll probably be using RXN quite a bit throughout this semester and throughout the year. Okay, so I just wanted to be able to focus in on that, and I'm going to zoom just a tad more. Okay, so what I'm going to do is show you 2 examples of molecular level changes here. A pretty simple reaction and one that's actually a famous reaction that had some implications for world famine and solving some of the problems worldwide. You don't hear about famines too often anymore, sometimes, but not like you used to, and part of it is because of this chemical reaction that I'm about to show you. Well, the second one. Okay, so what I'm going to do here is I'm getting a little bit ahead of myself from the book, doing a little bit more actually of chapter 3 right here, but that's fine. That will allow us to sort of rocket into chapter 3 a little bit more efficiently. So I'm going to show you 2 examples, and I can't do any demos here. It's not a safe place to do demos. So I may video some demos or show you just links to demos. You can look these up too. You type that into a search engine, electrolysis of water, you'll find tons of videos. So if my image that I have for electrolysis of water on the slide isn't sufficient, that's fine, go ahead and Google it. I actually have a neat demonstration that I do for this one. So electrolysis, lysis is to cut or split, and electro is electricity, so it's using electricity to split water. But what's it splitting it into? Hydrogen and oxygen gas, which are diatomic. H2 and O2, not H and O, H2 and O2. Remember your diatomics. H2, O2, N2, F2, Br2, all the halogens, group 17 on the periodic table. So memorize those. Okay, yeah, and I think there's a slide for this that shows it macroscopically. It's really cool. I have a neat demo, which I suppose I could do. So I'm at example 1 here on the slides. I really should be more explicit about this. This is example 1, electrolysis of water. And the sentence there is important. Eventually, we want you to be able to take that sentence, and I'm just going to read it off the slide. And you should write it down. Water is transformed into hydrogen gas and oxygen gas when an electric current is passed through it. Okay, that's a nice text description. We want to translate that into chemical symbols, and some of you can do that already, so go ahead. If you know what to do, go ahead and do that. I'm going to show pictures first, and then we'll put it into the more familiar chemical symbols. And I always seem to forget that I turned this on. And are we recording? Yeah, sorry about that. I'll probably do that every video. So we're electrolyzing specifically liquid water. So we basically hook up a battery. Oh, sorry, I forgot to finish my story. You can actually do this demonstration. Take a plastic cup, put some water in it and some salt, not much, to get the electrical current. Take 2 thumbtacks, push them through the bottom, metal thumbtacks, and take a 9-volt battery and touch it to the thumbtacks, and you'll see hydrogen and oxygen gas being given off. It's really kind of a cool demo. So I'm going to stick to the previous pictures that we had, maybe make them a little smaller. So we'll have 6. 1, 2, 3, well. So there's liquid water. Hopefully I said liquid water in the, oh, I said water, so that's typically referred to as H2OL. 1, 2, 3, 4, 5, 6. Excellent. And we are now going to hook it up to the battery, basically. And this is endothermic, going this direction. The molecules have to absorb energy from the battery, so this exterior source, that's endothermic, going in this direction. Oops, that's not right. So it's splitting it into, what did I say? Hydrogen gas and oxygen gas. So it's H2 gas and oxygen gas. So that's what's happening here. The trick is, how many of each? So H2, just look at it for a second. It looks like I could make it looks like I make 6 of those, couldn't it? I have 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 12 hydrogen atoms shown in the H2. So if I'm going to make those into H2 diatomics, I can make 6 of those. Because that would be 12 total atoms. Remember, you can't create atoms, you can't destroy atoms, you just change the form that they're in. So I would call diatomic hydrogen something like that. And I can only make as many atoms as I had over here. It's conservation of mass, conservation of energy, first law of thermodynamics, whatever you want to call it. So I can make 6 of those. 1, and it's a gas, and they're spread out all over the place. 2, 1, 2, 3, 4, 5, and I'll put them down here. And these are gases, so they're moving around. All right, and then O2, so somehow I can only make 3 of those, right? Because I've only got 6 oxygen atoms over here. So if I'm going to make O2, I can only do 3 of those. I'm trying to keep them the atoms the same size. And they're moving around. So they're in there and they're colliding and they're doing all that good stuff. Sorry, that's a really sloppy picture. Okay, so the way we symbolize this more chemically is we say H2O liquid reacts to produce, that's what the arrow means, H2 gas plus O2 gas. And let's just write the numbers in front. We're starting off here with 6 water molecules, and we're producing 6 H2s and 3 O2s. The subscript refers to the atom before in the molecule. The coefficient refers to the total number of molecules. So subscripts mean one thing, bonded together. Coefficients mean something else. So these 6 water molecules are not 6 water molecules bonded together as a cluster. They're 6 separate water molecules, 6 separate H2 diatomics, 3 separate O2 diatomics. And some of you see where we're going with this. The simplest way to represent this will be to reduce these coefficients down to their simplest ratio. A 6 to 6 to 3 ratio is better represented by a 2 to 2 to 1 ratio in its simplest form. And the 1 is understood. You can write the 1 if you like. So it's a 6 to 6 to 3, which reduces to a 2 to 2 to 1 ratio between those two. I think I sneak in some vocabulary here. Yes. So that is a coefficient. You might want to write, well, coefficient. I think that's spelled right. Oops. Coefficient. No, I didn't spell that right. Still waking up. That's a subscript, in case that wasn't obvious. The chemicals as they appear before a chemical reaction. These are called the reactants. Since there's only one here, there's a reactant, but if there's more than one, okay. These are called the products. And I'm going to run out of space. This is called a balanced chemical equation. It's balanced because the number of atoms on both sides are the same. It's a chemical equation because it's showing what did the chemicals look like before, what do they look like after. It's showing that the bonds are changing. Here it's bonds between oxygen and hydrogen, and over here it's just bonds between hydrogens themselves and oxygen themselves. So the bonds are changing, and there's a lot more to it than that. Okay, I think that's all I wanted to do with that example. And since we do it this direction, does anybody know what would happen if we took hydrogen gas and oxygen gas, put them in the same thing, and returned them to water? That's actually a demo I would never do. That's called combustion. And if you mix them in a 2-to-1 ratio and give it a spark to get it going, man, does it make a boom. It makes a huge, huge boom. And that is extremely exothermic. Extremely exothermic. Okay, so that's electrolysis. So you can see the picture on there. I think the picture on there is okay. It actually is a little bit different of a setup. It collects hydrogen gas in one inverted tube, oxygen gas in another inverted tube, at the anode and cathode. I don't think we have time to do electrochemistry in this course. But basically you're collecting twice as much hydrogen gas as oxygen gas. So one tube will have twice as much volume in it, that's the hydrogen, as the oxygen. So that's kind of a neat demo. So that's a way to introduce chemical changes and to build in a lot of other stuff. Reactants and products, balancing an equation. If you remember anything from a chemistry class, you balanced equations, and the only rule is you can only change the coefficients. You can't change the subscripts, that changes the chemicals. So you have to go back and forth and play around with the coefficients until you get it to balance. So here we have 4 hydrogen atoms, 2 oxygen atoms, 2 oxygen atoms. You have to account for subscripts and coefficients together. And the coefficient distributes to everything in the molecule, which is important when the molecule gets really big. Okay, the second example. And you can go ahead and try to write it down. Let's do the reverse. Let's actually write the chemical equation first before we do the cartoon picture. Because that's actually more important to me right now, is that you can take that sentence description and translate it into a balanced chemical equation. So we're taking hydrogen gas and nitrogen gas combined at high temperature in the presence of a catalyst, which speeds up the reaction, but it's not a reactant or a product, so it's not like we put plus catalyst, to produce ammonia, which is condensed as a liquid. Okay, let's just do the chemistry first, then I can talk a little bit about the history. So I'm actually gonna do this a little differently than my notes. Sometimes I like to not do everything exactly the way I have written out. So, yeah, we're gonna get to the same place. So we're gonna take hydrogen gas, and we know that it's diatomic. You've got to remember that. Please don't write just H. Plus nitrogen gas, diatomic, to produce ammonia, which we talked about last time. And it says it's condensed as a liquid, so let's just do that. We're going to work more on balancing equations later, but see if you can balance this. See if we have to change the coefficients. Well, you might not have to change them all. So maybe just stop the video for a second and see if you can change these coefficients and balance them. Again, we haven't really, this is not part of this lesson necessarily, but I'm getting ahead of myself. So do that, stop it, and see what you can do. I'm going to balance it now. So we've got 2 hydrogen atoms here, because there's a coefficient. We have 3 over here, that's Which is not a good place to start. Okay, well you may figure that out. It's 3 and 2. The least common multiple is 6, so you can figure that out. It may be easier to start here. There's 2 nitrogens and only 1 nitrogen here. So I have to put a 2 here. Yes, that 2 affects the hydrogen, but it actually works out in our favor. Now I've got 2 nitrogens and 2, but now I've got 6 hydrogen atoms. So if I come over here and put a 3, we should be good to go. So it should be 3, 1, 2 is how you would balance this. Okay, that's good. And let's do the cartoon picture. I'm going to do this one in reverse. So I'm going to put the products first. Okay, so here, this is your product. These are your reactants. Reactants go to products. And typically with a chemical equation, you might put the conditions, so increased temperature in the presence of a catalyst. But they're not involved in the reaction. And let's assume we are making 6 ammonias. Let's just, for argument's sake, just do 6. And you see where I'm going with this. Go back and draw the reactants picture. 4, 5, 6. Again, that's just an arbitrary number. We're trying to make 6. Liquid takes the shape of the container but has the specific volume. That's a liquid. And what would we be starting out with over here? Oh, that's a terrible box. It's supposed to be the same size. So, okay, so if we have 6 ammonias, looks like we can make 3. Is that right? Yeah, we can make 3 N2s. They kind of look like bow ties. Try to make them the same size. And those are gases, so that would look like this. They move around colliding. So we would have 3 N2 gases, just coming from working backwards. And hydrogen looks like we could make, how many of those could we make? Well, looks like we can make 9 of them, is that right? So we have 18 hydrogen atoms. So if we have 18 hydrogen atoms, we can make 9 diatomic hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't think I spread those out very well, but you can spread them out better. Okay, you get the idea. So, now normally I would start with this. So that's how you represent this one. It's a 9 to 3 to 6 ratio, which is the same thing as a better way of doing it is a 3 to 1 to 2 ratio. So you wouldn't leave it like this, you'd reduce it down to this one. And I think that's it. Okay, just a couple of comments. This is called the Haber-Bosch process on an industrial level. Fritz Harbor, I'm just going to tell a quick story here. Fritz Harbor was a German chemist. Interesting character, genius. Won the Nobel Prize in chemistry for some of his work. He also has some infamous history to him as well. He existed in the early 1900s and actually did a lot of chemistry for the Nazi war machine, including the pellets that were used to make gas that killed prisoners in the gas chambers. That gas was called Zyklone B. He wasn't the only chemist that developed that, but he was one that helped to develop those particular reagents, those pellets that did a lot of destruction, as I'm sure you know. Another thing he did, this is a complicated man, complicated scientist, is this process to take hydrogen and nitrogen and make massive quantities of ammonia was then used for fertilizer. So if you've gone around any farmland, when they're fertilizing their ground with ammonia, you'll sometimes see giant tanks called anhydrous ammonia, I think. So a lot of the water has been removed from the mixture, and they spray it all over the field. It smells terrible. But this is a cheap way to do fertilizing, and it really solved a lot of world hunger problems back in the day, and especially in the post-World War II era. So there are some pluses and minuses to his history. The Haber-Bosch process for producing ammonia was definitely a plus. Okay, next lesson, we're going to jump into more about the structure of the periodic table and the structure of atoms within the periodic table. So it's pretty traditional chemistry. What's an atom? Protons, neutrons, electrons. How do you know how many of each? So make sure you have this and you are ready to go, and we'll pick up with the next lecture.